we'll now take this example to see all the different cases that are present in the deletion of a binary search tree. As you see here, this is the first case where the node that needs to be deleted is simply the leaf node. So what happens here is we check the if condition and see that key less than root dot key, that is 20 is less than 50. So we go to the left subtree of 50. At 30, we check that 20 is less than 30. So we go to 20. At 20, we find out that 20 is neither less than root dot key or greater than root dot key, that is this is equal to 20. So we go to the left condition and we see that the first if condition is satisfied, that is root dot left is null, that is this value is obviously null. So we return the right value of this particular node, that is we return the null value of this particular node. So at 30 we go to 20 and at 20 we return null. So what this basically means is in this node both the values in the left in the subtrees are basically null. So we return either of these null values and this null value goes back to 30. So at 30 the root dot left value is now currently null. So we return this value back to, we return the root value of 30, we return we return 30 back to 50, and at 50 the tree will look like, the right subtree will remain the same and the left subtree will be 50 30 and this will be 40 31 and 41 and this value is going to be null. So that is the reason why we return the root value back to 50. So this is the first case. We'll now go to the second case where the node has at least one child, that is we are trying to remove 80. So we'll now see what's going to happen. We'll take this tree as the same example and we now know that 80 is greater than 50. So we go to 70 and 70 is greater than 80. So we know that key is greater than root dot key. So we go to this value and at 80 we find out that 80 is neither greater than root dot key nor less than root dot key, that is 80 is equal to this current value, and we find out that the left subtree of 80 is not null and the right subtree is null. Since the right subtree is null, we return the left value. So we are going to return node 71 back to 70. So at 70 what's going to happen is root dot right is now going to be 70 and the structure will be 70 and 71, because 70 that was pointing to 80 earlier here will now be pointing directly to 71. That is what used to be 70, 80 and 71 will now be 70 and 80 will be the same, but 70 will now be directly pointing to 71. So that is what has happened here. So the 80 over here has been completely removed. The reason why that happened, because we checked that 80, the left subtree of 80 was not null, so we returned it directly back to its parent node. So 70 is now going to be directly pointing to 71. Then that is going to be the right subtree, and that now we return the value of 70 back to 50. So at 50 what's going to happen is root dot right is equal to 50. So the traversal is 50, 70, 60 and 71. Now 80 is no more here. So that is the second case. So we are now going to delete a node that has two children, that is we are going to now delete node 30, and now we'll now see what's going to happen. So as we see here, we start from the root node and we see that 30 is less than node 50. So we go to the left subtree of node 30. So at 30 we find out that the first two if and else if conditions are unsatisfied. So we go to the third else condition and we find out that both the left and right subtree are not null. So what we are going to basically find here is we are going to find out the minimum value from the right subtree of root of right subtree of node 30 and then going to replace this value at node 30 by the value at node 31. So that is why we are calling the node min value function. So the root dot key value at node 30 will be 31, and that would be discovered using the min value function. The min value function basically does traversal down the entire subtree and finds out the smallest value, and this value now becomes 31. So the node at this point of time will be 31, 20, 40, 31 and 41. Since we however have two values over here, we need to delete this 31 present here. So we again call the same recursive function and then go down towards the same path. That is, we go down towards the right subtree of node 30, and at node 4 not node 30, at node 31 we go down towards the right subtree of node 31, and we go down since we know that the root dot key value is less than node 40, we go down towards node 40, and at 31 we find out that the two values, that is the key value and root dot key values, are the same, and we find out that the left and right subtrees are both of them are null. So we return one of the null values back to node 40. So at node 40 we have root dot left is equal to null, which means that the node 31 here has been completely removed, and 40 will now be pointing directly to null. So 40 null and 41 is how the structure will be, and the control, we return the root directly back to the parent node of 40, which is 31. So at 31 we have root dot right as 40, which is going to be 31, 20, 40, null and 41. So we now return null back to the parent node of 31, which is 50. We return the value of node 31 back to the parent node of 31, which is now 50. So at 50 the current node is going to be 50, 31, 20, 40, null and 41, and the right subtree is going to be the same, so I won't draw it again. And this value will again be assigned to root dot left, and so root dot left is now going to be 31, and we again earlier it used to be 30, now it's 31, that is, it contains the address of the node 31. So we now return this root back to the main program. So that is how deletion is done for the third case. Thank you.